There is something sitting at the edge of what we know, and it refuses to go away. Not a theory, not a hypothesis scrawled on a whiteboard by a sleep-deprived graduate student, not a ghost story whispered between astronomers at a conference bar at 2 in the morning. Something real, something measured, something that has been observed with the finest instruments human civilization has ever constructed, cross-checked by thousands of independent researchers across dozens of countries, replicated under conditions so controlled and so precise that the margin of error is smaller than the width of a hydrogen atom. And yet, by every law we have ever written about the universe, by every equation we have ever trusted to describe the fabric of reality, by every principle that has guided science for 4 centuries, it should not exist. You need to sit with that for a moment, not just absorb it as an interesting fact and move on to the next thing. Actually sit with it, because what you are about to encounter is not the kind of puzzle that makes scientists excited in a fun, curious way. It is the kind of puzzle that makes them go quiet, the kind that empties a room, the kind that causes a physicist who has spent 30 years building mathematical models of the universe to stare at a data set and say, in a voice barely above a whisper, that they do not understand what they are looking at. And the reason it matters, the reason this is not just an academic curiosity, is that if this thing exists, then everything we think we know about reality is either incomplete or wrong, or something far stranger than either of those words can adequately describe. You have been told your entire life that science is the most reliable method humans have ever invented for understanding the universe, and that is true. It is magnificently, beautifully true. The scientific method, this disciplined, self-correcting, evidence-driven process of asking questions and testing answers, has given us antibiotics and airplanes and the internet and the ability to detect gravitational waves from 2 black holes colliding 1 billion light-years away. It has decoded the language of DNA, mapped the architecture of atoms, and traced the entire history of the universe backward in time to within a fraction of a second after the Big Bang. Science works. It works better than anything else we have. And that is precisely what makes this so deeply unsettling. Because science, when confronted with what we are about to discuss, does not have an answer. It has theories. It has models. It has proposed explanations that range from brilliant to desperate. But an answer? A clean, settled, universally agreed upon answer? No, it does not have that. To understand why this is so disorienting, you first need to understand what the universe is supposed to look like from the inside. You need to understand the architecture of certainty that scientists have spent centuries constructing. Because that architecture is genuinely beautiful. It is not arrogant or blind. It is a cathedral built from evidence, and every stone in its walls has been tested and tested and tested again. The laws of physics are not suggestions. They are not guidelines. They are the deepest patterns we have ever found buried in the behavior of matter and energy in space and time. They describe a universe that is, at its core, ordered, predictable, lawful, a universe where the same cause always produces the same effect, where nothing appears from nothing and nothing vanishes into nothing, where information cannot travel faster than light and the present cannot be influenced by the future. Think about what that means. Causality, the iron principle that causes precede effects, is not just a law of physics. It is the skeleton of reality as we experience it. It is why your coffee gets cold after you pour it, not before. It is why the crack in a windshield spreads outward from the point of impact, not inward toward it. It is why the glass on the floor does not leap back up and reassemble itself into a smooth, unbroken surface. Every story the universe tells is a story that moves in one direction, forward. From past to present to future, from cause to effect, from the initial condition to the outcome. That directionality is not something scientists imposed on the universe from outside. They found it there, embedded in every measurement, every observation, every experiment. The universe itself insists on it, and for centuries that insistence seemed absolute. Then there is the conservation of energy, one of the most beautiful principles in all of physics. The idea that the total amount of energy in a closed system never changes. It can transform from kinetic to thermal to electromagnetic to chemical, but the total, the grand sum, always remains the same. You cannot create energy from nothing. You cannot destroy it into nothing. It flows, it converts, it redistributes, but it never appears or disappears. This is not just a rule written in textbooks. It is something confirmed in every laboratory, every particle accelerator, every astrophysical observation ever made. The conservation of energy underpins chemistry, thermodynamics, nuclear physics, quantum mechanics, general relativity. Pull it out of the foundation, and the entire edifice collapses. And yet, And yet there is something about the universe on the largest scales, something confirmed by multiple independent lines of evidence, that makes physicists whisper to each other that maybe, just maybe, energy conservation might not be the absolute truth they thought it was, and the speed of light, the ultimate speed limit, the absolute ceiling on how fast anything can move through space, how fast any signal can travel, how fast information can propagate from one point to another. Einstein built his entire theory of special relativity on this single strange fact. The speed of light in a vacuum is the same for all observers, regardless of how fast they are moving. It is 300,000 kilometers per second, and nothing, no particle of matter, no signal, no influence of any kind, can exceed it. This is not just a limitation of our current technology. It is built into the geometry of space-time itself. Exceeding the speed of light would not just be technically difficult, it would require breaking the structure of space and time in ways that would make causality itself impossible. Effects would precede their causes. The future would influence the past. Time would lose all meaning. The universe as we understand it would unravel. And yet quantum mechanics, our most precisely tested theory of physical reality, contains something that seems at first glance to violate this principle in a way that is so disturbing that Einstein himself called it spooky and spent the rest of his life trying to prove it could not be real. These three pillars, causality, conservation, the speed limit of light, are not isolated rules. They are woven together into a single coherent picture of a universe that makes sense, a universe that follows rules, a universe that, no matter how complex or counterintuitive it might seem at the quantum scale or the cosmological scale, ultimately behaves according to principles that can be written down, tested, and trusted. For a long time, the greatest minds in human history looked at this picture and felt something close to satisfaction. Not the kind of satisfaction that comes from solving a puzzle and putting it away, the kind that comes from standing in front of a vast, intricate tapestry and realizing that every thread connects, that the whole thing holds together, that it makes sense, and then they found something it could not explain. The first time you hear about quantum entanglement, it sounds like science fiction. It sounds like the kind of thing someone invented for a movie about teleportation, or a novel about mind reading, or a philosophical thought experiment designed to make first-year students feel dizzy. Two particles become entangled. You separate them by any distance you choose, a meter, a kilometer, a million light years. You measure one of them, and at the exact moment you do, the other one, instantaneously, without any signal passing between them, without any physical connection of any kind, assumes a correlated state, not after a delay, not after a signal travels at the speed of light from one to the other, instantaneously. The word physicists use is non-local. The two particles behave as though they are part of a single system, regardless of the distance between them. And this is not a theory. This is not a prediction that still needs to be tested. It has been tested, over and over and over again, with photons, with electrons, with atoms, with molecules, in laboratories, in space, across distances stretching to thousands of kilometers. The results are always the same. The correlation is always there. The instantaneous connection is always there. You might be thinking, but wait, scientists always say that entanglement cannot be used to send information faster than light. That is true, and that caveat is important. But the fact that you cannot use entanglement to send a message does not make it any less strange. It does not make it any less of a violation of everything intuitive about how the universe is supposed to work. Because what entanglement tells you, what it cannot help but tell you, is that the universe is non-local. That two particles on opposite ends of the observable universe can be connected in a way that has no precedent in classical physics. That the separation we experience between distant things, the vast, empty, unbridgeable distances of space, is, at some level, not as real as it looks. And if the separation is not as real as it looks, then what is space, exactly? What are you exactly when you think of yourself as a thing located in a particular place? These are not rhetorical questions. They are the kinds of questions that physicists who work on the foundations of quantum mechanics actually spend their careers trying to answer, and they are not close to an answer. But entanglement, as unsettling as it is just the beginning, because there is something deeper lurking beneath it, something that entanglement is merely a symptom of. And to understand that deeper thing, you have to go back to the most famous, most contentious, most philosophically explosive experiment in the history of physics, the double-slit experiment. If you have heard of it before, set aside whatever you think you know about it, because there is a layer to this experiment that most people never reach. A layer that most people never think about, because thinking about it clearly leads you to a place where the foundations of reality start to feel genuinely precarious. The setup is simple enough that you could build it in a high school classroom. You shine light, or electrons, or atoms, or any quantum particles, at a barrier with two narrow slits cut into it. Behind the barrier, you have a detector screen that records where the particles land. If particles behaved like tiny billiard balls, you would expect to see two bands on the detector screen, one behind each slit, where the balls passed through. What you actually see is an interference pattern, a series of alternating bright and dark bands spread across the screen, just like the pattern you would see if you dropped two stones into a pond and watched the ripples interact. This interference pattern tells you that the particles are behaving like waves. They are passing through both slits simultaneously. They are interfering with themselves. And this is already strange. This is already a particle being in two places at once. But it is not the strangest part. The strangest part is what happens when you try to find out which slit the particle went through. When you add a detector, any kind of detector, any physical apparatus that could in principle record which path the particle took, the interference pattern vanishes. The particles stop behaving like waves and start behaving like billiard balls again. The simple act of measuring which slit they go through, the simple act of an observer gaining information about the path, changes the outcome of the experiment. The particles were in a superposition, a genuine simultaneous existence in multiple states, and the act of observation collapsed that superposition into a single definite state. This is not a theoretical prediction. This is an experimental fact, tested thousands of times, never contradicted, and it implies something that should make you feel the ground shift slightly beneath you. The act of observation, the acquisition of information, plays a role in determining what reality is, not in the sense that we see things and name them, in the literal sense that the physical outcome of an experiment depends on whether information about it is recorded by any physical system anywhere in the universe. Now, physicists have spent nearly a century developing frameworks to make sense of this. The Copenhagen interpretation says that the wave function, the mathematical description of a quantum system, collapses when it is measured, but does not take a definitive position on what the wave function actually is or what the collapse actually means. It is, famously, the interpretation that says, shut up and calculate, use the math, make the predictions, do not ask what is happening underneath. And for most practical purposes, it works. The predictions are staggeringly accurate. Quantum mechanics is the most precisely verified theory in the history of physics. Its predictions have been confirmed to more decimal places than any other theory ever devised. But the interpretational questions, the questions about what is actually happening beneath the formalism, what reality actually looks like between measurements, those questions remain open, viciously, embarrassingly, profoundly open. There is the many worlds interpretation, proposed by Hugh Everett in the 1950s, which says that the wave function never collapses. Instead, every possible outcome of every quantum measurement actually occurs in a constantly branching universe. When you flip a quantum coin, the universe splits. In one branch, it lands heads. In the other, it lands tails. Both branches are equally real. Both versions of you exist. The universe is not a single thread of events, but an infinite, ever-proliferating tree of all possible histories. This interpretation preserves the mathematical elegance of quantum mechanics perfectly. It requires no arbitrary rule about collapse, but it requires something in return: the existence of an unimaginably vast, in fact infinite, number of parallel universes, none of which can ever communicate with or be detected by any of the others. You cannot falsify it. You cannot confirm it. You can only accept it or reject it on the basis of your philosophical preferences, which is not exactly the kind of thing scientists are supposed to do. There is pilot wave theory, also called Bohmian mechanics, which says that particles always have definite positions, but are guided by a real physical wave that spreads through all of space simultaneously and determines their trajectories. This interpretation is completely deterministic. In Bohmian mechanics, there is no randomness at the fundamental level, no collapse of the wave function, no superposition of physical states. Everything that happens is the result of hidden variables, precise initial conditions that we do not have access to, but which in principle fully determine all outcomes. It reproduces all the predictions of standard quantum mechanics perfectly, but it requires a wave that is instantaneously non-local across the entire universe, a wave that can influence a particle in one place by changing conditions somewhere else, right now, across any distance. And this non-locality is so extreme, so pervasive, so fundamental to the theory that many physicists find it deeply disturbing, because it means that even in the most deterministic version of quantum mechanics, the universe is not made of separate, independent things. It is more like a single, indivisible thing that we keep mistakenly perceiving as made of parts. And then there is the relational interpretation, proposed by Carlo Rovelli, which says that quantum states are not properties of systems in themselves, but only relative to other systems. A particle does not have a definite position except relative to some other physical system. There is no God's eye view of the universe, no objective observer independent description of reality. The universe is a web of relationships, and what we call facts are actually facts relative to some perspective, some physical system, some interaction. This interpretation is elegant and consistent. It avoids many of the paradoxes of the other interpretations, but it leaves you with something even more unsettling than the paradoxes it avoids. The idea that there is no observer-independent reality, that the universe does not have a single, definite description, that what is real is always relative to something, to some perspective, to some interaction. And if that is true, then the question of what the universe is like when nothing is looking at it, when there is no perspective, no relationship, no interaction, may not even be a meaningful question. You are now somewhere in the middle of the labyrinth, and you may have noticed that every path through it leads to a wall. Pick any interpretation of quantum mechanics you like, and there are more than the four just mentioned, each with its own paradoxes and demands, and you will find that it requires you to accept something that conflicts violently with your intuitions about reality. The Copenhagen interpretation requires you to believe that physical systems do not have definite states until they are measured, which means that the moon might not be in a definite position when no one is looking at it. The many worlds interpretation requires you to believe that an infinite number of parallel universes exist, branching off from every quantum event, forever. Pilot wave theory requires you to believe in a non-local field that instantaneously influences every particle in the universe. Relational quantum mechanics requires you to believe that there is no objective, observer, independent reality. Every door in this labyrinth opens onto a different kind of impossible, and the reason is not that physicists have not tried hard enough. The reason is that something very deep, something at the very bottom of what we know, does not add up. The universe is trying to tell us something, and we do not have the ears to hear it yet. But quantum mechanics, as philosophically vertiginous as it is at least a field where scientists have had decades to build their frameworks of uncertainty. They know it is strange. They have internalized the strangeness, institutionalized it, built entire departments and careers around navigating it. What is harder to absorb, what produces in physicists something closer to raw, unmediated discomfort, is what has been discovered in the past few decades at the opposite end of the scale. Not in the infinitely small, but in the infinitely large. Not at the quantum level, but at the cosmological level. Because the universe, as we have mapped it in the last 30 years, contains something that should not be there. Something that constitutes nearly 70% of everything that exists. Something that is driving the universe apart with increasing speed. Something that we cannot see, cannot directly detect, cannot explain by any mechanism we have ever understood. We call it dark energy. And the more carefully you look at it, the more deeply strange it becomes. Here is the discovery that changed everything. In 1998, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were doing something that sounded routine. They were measuring the distances to a particular type of supernova, a type Ia supernova, which astronomers use as what they call standard candles. Because every type Ia supernova explodes with approximately the same intrinsic brightness, you can measure how bright it appears from Earth and calculate exactly how far away it is. The teams were using these supernovae to measure how the expansion of the universe was changing over time. The assumption, the safe, theoretically grounded, cosmologically standard assumption, was that the expansion was slowing down. Gravity, the inward pull of all the matter in the universe on all other matter, should be decelerating the expansion. The universe should be like a stone thrown upward, still moving, but slowing down, being pulled back by the weight of its own gravity. The only question the teams expected to answer was, by how much? What they found instead was that the expansion was not slowing down, it was speeding up. The universe was not decelerating under the pull of gravity, it was accelerating. Something was pushing outward, something was driving galaxies apart at an ever-increasing rate, and that something was not in any of the equations. It was not predicted by general relativity in its standard form. It was not predicted by any model of the universe that anyone had been working with. It came entirely out of nowhere. Perlmutter, Schmidt, and Rees won the Nobel Prize in Physics in 2011 for this discovery. But a Nobel Prize does not explain what dark energy is. It just confirms that someone found it. And 25 years later, after countless additional observations, after building entire orbiting telescopes dedicated to mapping its effects, after running supercomputer simulations of the entire history of the universe trying to model its behavior, we still do not know what it is. The most straightforward mathematical description of dark energy is something called the cosmological constant. Einstein actually introduced this term into his equations of general relativity in 1917, before the universe was known to be expanding. He needed it to make the equations describe a static universe, because without it, his equations predicted that space should be either expanding or contracting. When Hubble discovered in 1929 that the universe was expanding, Einstein reportedly called the cosmological constant his greatest blunder and removed it from his equations. But when dark energy was discovered in 1998, the cosmological constant was brought back, because if you add it into Einstein's equations with the right value, it naturally produces accelerating expansion. So in that sense, it fits. The math accommodates it. But accommodating something mathematically is not the same as understanding it physically, and the physical interpretation of the cosmological constant is where things become genuinely disturbing. The cosmological constant corresponds physically to something called vacuum energy, the energy of empty space itself. In quantum mechanics, the vacuum is not truly empty. It is a seething, roiling sea of quantum fluctuations, virtual particles constantly flickering in and out of existence, borrowing energy from the future to exist briefly in the present before annihilating each other and returning what they borrowed. This is not speculation. This is a measurable effect. The Casimir effect, a tiny but real and reproducible force between two uncharged metal plates placed very close together in a vacuum, is a direct consequence of vacuum energy. So the vacuum has energy. That much is confirmed. The problem is the amount. When physicists calculate the expected vacuum energy density using quantum field theory, the best theoretical framework they have for understanding quantum particles and their interactions, they get a number. And when they compare that number to the observed value of the cosmological constant derived from the supernova data and all other cosmological observations, there is a discrepancy. Not a small discrepancy. Not the kind of discrepancy that gets resolved by a more careful measurement or a slight adjustment to a parameter. The discrepancy is 120 orders of magnitude. That means the theoretical prediction and the observed value differ by a factor of 10, followed by 120 zeros. This is, by a staggering margin, the largest discrepancy between a theoretical prediction and an experimental observation in the entire history of science. It is so large that physicists have a name for it. They call it the worst prediction in physics. Some call it the vacuum catastrophe. Some call it the cosmological constant problem. All of them, in their most honest moments, call it something they do not understand. Let that number wash over you for a moment. 120 orders of magnitude. To give you a sense of how incomprehensibly large that is, the ratio of the size of the observable universe to the size of a proton is only about 40 orders of magnitude. The ratio of the age of the universe in seconds to the Planck time, the smallest meaningful unit of time in physics, is about 60 orders of magnitude. And the discrepancy between the theoretical prediction and the observed value of dark energy is twice both of those numbers combined. If quantum field theory is telling us the truth about vacuum energy, then either something cancels that enormous energy density to produce the tiny cosmological constant we observe, some mechanism of extraordinary precision that we have never found and cannot explain, or quantum field theory is wrong in some way we do not understand, or something else entirely is going on, something we have not conceived of, something outside the boundaries of every framework we have. And here is the part where your instinct for rational reassurance will try to step in. You will want to say, well, the discrepancy just means we have made an error in the calculation. Our model of vacuum energy must be wrong. We just need to fix the theory and the problem goes away. And maybe that is true. Many physicists hold exactly that position. But the problem is that fixing the theory in the required way is not straightforward. It would require a level of fine-tuning, a level of precise cancellation between different contributions to the vacuum energy that physicists find extremely unnatural. When you need a physical quantity to be zero or near zero due to a precise cancellation between two enormous numbers, and there is no symmetry or mechanism to enforce that cancellation, you have what is called a fine-tuning problem. You need the positive contributions to vacuum energy and the negative contributions to cancel each other to an accuracy of 120 decimal places. with no explanation for why they should cancel so perfectly. And in physics, when something is fine-tuned without explanation, it is usually a sign that you are missing something fundamental. But the cosmological constant problem is not the only thing about dark energy that should trouble you. There is something else, something that might actually be more disturbing depending on how you think about it. Dark energy is not just some background quantity that scientists measured and filed away. It is actively doing something. It is causing the universe to expand faster and faster. Right now, at this moment, every galaxy in the universe that is far enough away is receding from us at an accelerating rate. Some of them are already receding faster than light, not because anything is moving through space faster than light, but because the space between us and them is expanding so rapidly that the distance grows faster than light can cover it. And as the universe continues to accelerate, more and more of it will pass beyond the cosmic horizon, the boundary beyond which nothing can ever reach us, because the space between us and it is expanding too fast for any signal to cross. In billions of years, if dark energy continues to behave as it currently does, the universe will become an increasingly lonely place. Every galaxy beyond our local group will disappear over the horizon. The observable universe will shrink and shrink and shrink, and in the far, far future, any civilization that exists will look out at the night sky and see only their own galaxy, surrounded by an infinite darkness, with no evidence that any other galaxies or stars or cosmic structures ever existed. They will have no way of knowing what we know now, simply because they will have been born too late. That last thought is worth dwelling on, not for its melancholy, but for its epistemological weight. It means that the information available to future astronomers will be less than the information available to us right now. The universe is, in a very real sense, hiding its own history. The evidence of the Big Bang, of the large-scale structure of the cosmos, of the hundreds of billions of galaxies that currently populate the observable universe, all of that will eventually be erased from the sky. This is not a metaphor. It is a direct consequence of accelerating expansion, and it forces a question that cuts very close to the bone of scientific confidence. If the universe can hide its own past from future observers through the simple mechanism of expansion, what else might it be hiding from us right now? What evidence of what truths might already have passed beyond our horizon? What features of reality might we be unable to detect, not because our instruments are not good enough, but because the geometry of space-time itself prevents those features from ever reaching us? We are not done with the large scale yet, because while dark energy is the most numerically extreme anomaly in all of physics, it is not the most recent, and it is not the most actively contested. There is something happening in modern cosmology that is, if anything, producing more immediate anxiety among working physicists. Something that is not about the distant past or the far future, but about the universe right now, this moment, measured with the best instruments we have. It is called the Hubble tension. And if you have not heard of it, you are about to understand why physicists are losing sleep over it. The Hubble constant is one of the most fundamental quantities in cosmology. It describes the current rate of expansion of the universe. How fast, on average, 2 points in the universe are moving apart due to the expansion of space. It has the units of kilometers per second per megaparsec, which means, for every megaparsec of distance between 2 points, they are receding from each other at this many kilometers per second. For decades, measuring this number accurately was one of the central challenges of observational astronomy. It required building space telescopes, calibrating distance ladders, measuring Cepheid variables, and type Ia supernovae across billions of light years. It was difficult, painstaking work. But eventually, after enormous effort and ingenious methodology, two independent methods converged on their answers, and the answers did not agree. The first method uses the cosmic microwave background, the faint afterglow of the Big Bang, the oldest light in the universe, a bath of microwave radiation filling all of space that encodes in extraordinary detail the state of the universe, just 380,000 years after the Big Bang. The Planck satellite, operated by the European Space Agency, mapped this radiation to unprecedented precision. By feeding that map into the standard cosmological model and running the clock forward to the present, cosmologists could predict what the Hubble constant should be today. Their answer was approximately 67 kilometers per second per megaparsec. The second method measured the Hubble constant directly in the late universe, using the distance ladder of Cepheid variable stars and type Ia supernovae. This is the method pioneered by the teams that discovered dark energy. refined over decades, and most recently brought to new precision by the Hubble Space Telescope's key project and related surveys. Their answer was approximately 73 kilometers per second per megaparsec, 67 versus 73. It does not sound like much, a difference of 6 kilometers per second per megaparsec, but the critical issue is not the size of the difference, it is the statistical significance. Both measurements have been made with extraordinary care, and the uncertainties in each measurement have been shrunk to the point where the two values are statistically incompatible. They cannot both be correct simultaneously, and new, independent measurements using completely different methods, gravitational lensing time delays, observations of bright megamasers in distant galaxies, gravitational waves from binary neutron star mergers, keep producing values that cluster around one or the other number. The universe seems to be giving different answers to the same question depending on how you ask it, and that is not how the universe is supposed to work. There are really only a handful of explanations for the Hubble tension, and none of them are comfortable. The first is that both measurements are right, and one of them has a systematic error, some bias in the data or the methodology that has not been identified. This is the most conservative possibility. It is the one that requires the least upheaval, and it may be true. But as the error bars have shrunk, and the independent confirmations have accumulated, this explanation has become progressively harder to maintain. The tension has not gone away as the measurements have improved. If anything, it has gotten sharper. The second explanation is that the standard cosmological model, the lambda CDM model, the model built on the cosmological constant and cold dark matter, the model that successfully explains the cosmic microwave background, the large-scale structure of the universe, the history of star formation, and countless other observations, is missing something important, something that changes the expansion history of the universe in a way that reconciles the two measurements. And the third explanation is the most disturbing, that there is something genuinely new in the physics of the universe, something that breaks the standard model in a way we have not yet identified. To illustrate how deep this might go, some proposed solutions to the Hubble tension involve introducing new physics in the early universe, a brief period of accelerated expansion before recombination, driven by some new form of energy called early dark energy, that would change the sound horizon scale baked into the cosmic microwave background and bring the two Hubble constant measurements into agreement. Other solutions involve new interactions for dark matter, or new species of neutrinos, or modifications to gravity itself. The problem is that these solutions are not free. Each one of them modifies not just the Hubble constant, but a cascade of other cosmological observables. Fix the Hubble tension with early dark energy, and you create new tensions in other measurements. Fix it with modified gravity, and you create problems for the growth rate of large-scale structure. Every proposed solution creates new wounds as it heals the original one. The patient keeps bleeding from different places, and the doctors are beginning to wonder whether it is not a series of separate injuries, but a single deeper problem they have not found yet. And then there is dark matter. We should talk about dark matter, not because it is the most mysterious thing in this story. We have already covered some stiff competition for that title, but because dark matter is the thing that has been with us the longest. The anomaly that has been sitting in the background of cosmology for nearly a century, quietly refusing to be explained, patiently waiting for us to develop instruments sophisticated enough to take it seriously. The first hint came in the 1930s, when astronomer Fritz Zwicky was studying the Coma cluster, a massive cluster of galaxies. He measured the velocities of the galaxies within the cluster and calculated how much mass would be needed to gravitationally hold them together. The mass he inferred from the dynamics was vastly larger than the mass he could see in the form of stars and gas. He called the missing mass dunkle materie, dark matter. And then for decades, most astronomers assumed he had made an error and moved on. In the 1960s and 1970s, Vera Rubin and Kent Ford were measuring the rotation curves of spiral galaxies, the way the orbital velocity of stars changes with their distance from the galaxy's center. According to Newtonian gravity and general relativity, the orbital velocity should decrease with distance from the center once you are past most of the galaxy's visible mass, just as the orbital velocity of the planets in the solar system decreases with distance from the sun. But Rubin and Ford found that the rotation curves of spiral galaxies are flat. The orbital velocity stays roughly constant all the way to the edges of the galaxy and beyond. The only way to explain this is if there is a vast halo of invisible mass surrounding every spiral galaxy, extending far beyond the visible disk of stars. This invisible mass, dark matter, had to be there. Its gravitational effects were undeniable, but no one could see it. No one could detect it with any conventional instrument. No telescope, no matter what wavelength it operated in, could find it, because dark matter does not emit light, does not absorb light, does not interact electromagnetically in any way we have been able to detect. It only interacts through gravity, and gravity, it turns out, is the hardest force to use as a detection tool at the scale of individual particles. Over the following decades, the case for dark matter became overwhelming. The large-scale structure of the universe, the vast cosmic web of filaments, voids, clusters, and superclusters that you see when you look at simulations of the universe on the grandest scales, makes sense only if dark matter exists. Without dark matter, the ordinary matter in the universe would not have had enough gravitational pull to clump together into the galaxies and clusters we see. The primordial fluctuations in the early universe, the tiny variations in density that seeded all structure, were too small on their own. Dark matter amplified them. Dark matter provided the scaffolding around which ordinary matter collapsed. The simulations run with dark matter in them look like the actual observed universe. The simulations run without it do not. The cosmic microwave background maps fit the model with dark matter beautifully. They do not fit without it. So dark matter is real, almost certainly real. But what is it? For decades, the leading candidate was something called a WIMP, a weakly interacting massive particle. WIMPs were theoretically motivated, arising naturally from supersymmetry and other extensions of the standard model of particle physics. They had the right properties to account for the observed dark matter density. They would interact with ordinary matter very weakly, through the weak nuclear force, making them extraordinarily difficult to detect but not impossible. And starting in the late 20th century, physicists built some of the most extraordinary detection experiments in history to find them. Detectors placed deep underground, shielded from cosmic rays and background radiation, filled with tons of ultra-pure liquid xenon or germanium, capable of detecting the tiny recoil of a nucleus hit by a passing dark matter particle. The experiments ran for years, then decades. They were upgraded, scaled up, made more sensitive, filled with larger and larger volumes of detector material. The Xenon experiment, the LUX experiment, the Pandax experiment, the LZ experiment. Each one an engineering masterpiece. Each one capable of detecting an interaction rate of less than 1 event per ton of detector material per year. Each one placed in mines so deep underground that the rock above filtered out nearly every known background particle. And each one came back with the same answer. Nothing. No WIMPs, no signal, no detection. The silence from these experiments has become deafening. The parameter space where WIMPs were supposed to exist has been carved away with extraordinary precision, and they are not there. Either they do not exist, or they interact so weakly with ordinary matter that even these extraordinary detectors cannot find them. And if they interact that weakly, the question becomes, in what meaningful sense are they a solution to anything? The particle accelerators have been equally unhelpful. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, was supposed to produce dark matter particles in its collisions. Supersymmetric particles, the theoretical partners to the known particles of the Standard Model, were expected to appear at energies accessible to the LHC. They did not. Not a single supersymmetric particle has been detected at the LHC in more than 15 years of operation. This does not prove that supersymmetry is wrong. Absence of evidence is not always evidence of absence, but it has pushed the theoretical mass of supersymmetric particles to ranges that make them progressively harder to justify as solutions to the dark matter problem. The WIMP miracle, the beautiful coincidence that made WIMP seem like the natural answer, is starting to look less like a miracle and more like a mirage. So physicists have pivoted. If not WIMPs, then what? The alternatives are numerous and they range from the conservative to the radical. There are axions, extremely light particles originally proposed to solve a different problem in particle physics, the strong CP problem, but which also happen to be good dark matter candidates. There are sterile neutrinos, hypothetical particles similar to the known neutrinos, but with no interactions except gravity. There are primordial black holes formed in the very early universe before any stars existed, which could account for some or all of the dark matter. There are ultralight axion-like particles, sometimes called fuzzy dark matter, which have such tiny masses that their quantum wave functions are enormous, giving dark matter an almost wave-like character on astrophysical scales. And then there is the most radical alternative of all. Maybe dark matter does not exist as a particle. Maybe what we call dark matter is actually a sign that our theory of gravity is wrong at certain scales. This last possibility, modified gravity, has a long and contentious history. The most prominent version is called MOND, modified Newtonian dynamics, proposed by physicist Mordechai Milgram in 1983. MOND modifies Newton's second law at very low accelerations, the kind experienced by stars at the outer edges of galaxies. In the regime where accelerations drop below a certain critical value, gravity becomes stronger than Newtonian mechanics predicts. And in this regime, without any dark matter at all, MOND reproduces galaxy rotation curves with remarkable accuracy, not just for some galaxies, for galaxy after galaxy after galaxy across a huge range of galaxy types and masses. The correlation between the mass distribution of visible matter and the observed rotation curve predicted by MOND is tighter and more consistent than anything predicted by standard dark matter models. This is not a trivial success. It is striking enough that a significant minority of astrophysicists take it seriously, even though the mainstream does not. But MOND has a serious problem. While it works beautifully for individual galaxies, it struggles with galaxy clusters, the very scale where Zwicky first identified dark matter. The dynamics of galaxy clusters, the way they distort space and bend light, the way the hot gas within them behaves, all require more mass than MOND provides from visible matter. And the most dramatic failure of MOND is the bullet cluster, two clusters of galaxies that collided and passed through each other. The hot gas in each cluster, which constitutes most of the ordinary matter, was slowed down by electromagnetic interactions during the collision and lagged behind. But when astronomers mapped the distribution of mass using gravitational lensing, measuring how the clusters bent the light from background galaxies, they found that most of the mass had passed through the collision without slowing down, as if it were invisible and non-interacting. The mass map matched what you would expect from dark matter particles sailing through each other unimpeded. It did not match any modified gravity theory. The bullet cluster is probably the single most compelling piece of evidence that dark matter is real as a substance, not just an artifact of wrong gravity. And so you are caught between two impossibilities. Either dark matter exists as a real substance, some new kind of particle or particles that make up 27% of the universe, and every dedicated experiment to detect it directly has so far failed completely, or dark matter does not exist, and our theory of gravity is wrong in a way that varies with scale and context in a manner that no consistent relativistic theory has yet managed to cleanly reproduce. Both possibilities are deeply uncomfortable. Both require something fundamental to be missing from our picture of physics, and both have been the subject of intense theoretical effort for decades without producing consensus. The field is not converging on an answer. It is fracturing into competing camps, each with its own preferred candidate and its own preferred evidence, none able to deliver the knockout observation that settles the question. You might be noticing a pattern by now, and the pattern is this. Every time scientists look at the universe at a new scale, with a new instrument, through a new theoretical lens, they find something that does not fit. Quantum mechanics refuses to reconcile with general relativity. Dark energy refuses to be explained by any natural physical mechanism. Dark matter refuses to be directly detected. The Hubble tension refuses to go away. Each of these is not just a puzzle to be solved. Each of them is a signal. A signal that the map we are using to navigate the territory of reality is missing something. Not something small and peripheral, something central and foundational. Let us go deeper. Let us talk about the thing that sits at the very bottom of this tower of anomalies. The thing that, when physicists try to confront it honestly and directly, produces in many of them a kind of controlled philosophical vertigo. The thing that has been called the deepest problem in physics. Not dark energy, not dark matter, not the Hubble tension. Something older and more fundamental than all of them. The problem of quantum gravity. The failure, after a century of trying, to reconcile the two greatest theories in physics into a single coherent description of reality. General relativity describes gravity. It describes the large-scale structure of space and time. It tells you how mass and energy curve spacetime, how that curvature determines the paths of objects moving through it, how the universe as a whole expands and evolves. It is a theory of smooth, continuous spacetime geometry. In general relativity, space is not a background against which things happen. It is a dynamic, flexible, physical entity that bends and stretches and ripples. And it is smooth. At every scale, no matter how small, the geometry of spacetime is a well-defined, differentiable manifold. There are no gaps, no discontinuities, no fundamental discreteness, just smooth, curved geometry all the way down. Quantum mechanics, and its more complete cousin, quantum field theory, describes everything else. It describes the behavior of matter and energy at the smallest scales. It tells you about electrons and quarks and photons and the strong nuclear force and the weak nuclear force. It is a theory of discrete, probabilistic, non-local quantum states. In quantum mechanics, physical systems do not have definite properties until they are measured. They exist in superpositions of states. They tunnel through barriers that classical physics says they cannot cross. They entangle with each other in ways that have no classical analog. And the energies and momenta of particles are quantized. They come in discrete packets, not continuous values. Both theories are spectacularly successful in their respective domains. General relativity has been tested to extraordinary precision in the solar system, in binary pulsar systems, in the detection of gravitational waves. Quantum field theory has produced predictions verified to more decimal places than any other theory in history. Each theory in its own domain is the most accurate description of nature ever achieved, and they are fundamentally incompatible with each other, not just technically difficult to combine. Philosophically, structurally, at the level of their basic assumptions, they contradict each other. General relativity assumes that space-time is smooth and continuous. Quantum mechanics assumes that things are fundamentally discrete and probabilistic. General relativity is a deterministic theory. Quantum mechanics is irreducibly probabilistic. In general relativity, the background of space-time is fixed, or rather determined by the distribution of mass and energy. In quantum mechanics, the state of a system is determined by measurement and probability. When you try to apply quantum principles to space-time itself, when you try to build a quantum theory of gravity, you get infinities. Not the ordinary infinities that crop up in quantum field theory and are handled by a mathematical technique called renormalization. Renormalization works for electromagnetism, for the weak force, for the strong force. It does not work for gravity. The infinities in quantum gravity are non-renormalizable. They cannot be absorbed into a finite number of parameters. They propagate and multiply and overwhelm the theory. The mathematics breaks down completely. This breakdown happens at a very specific scale called the Planck scale. Lengths of about 10 to the minus 35 meters, times of about 10 to the minus 43 seconds, energies of about 10 to the 19th giga electron volts. At this scale, the quantum fluctuations of spacetime itself become so violent that the very concept of smooth, continuous space ceases to have meaning. Below the Planck scale, and if there even is a below, if space and time even have meaning at that scale, our physics contains nothing. No theory, no equations, no description at all, just a region of utter theoretical darkness, where our two best theories simultaneously predict that they are both wrong and offer nothing to replace themselves with. String theory was supposed to fix this. For decades, it was the leading candidate for a theory of quantum gravity. The basic idea is that the fundamental constituents of nature are not point particles, zero-dimensional objects, but tiny, vibrating strings of energy. Different vibrational modes of these strings correspond to different particles, and crucially, one of the vibrational modes corresponds to the graviton, the hypothetical particle that carries the gravitational force. In this way, string theory naturally incorporates gravity alongside the other forces. It avoids the non-renormalizability problem of point particle quantum gravity. The infinities that plague the standard approach are smoothed out by the extended nature of strings, by the fact that they have a physical size, and their interactions are spread out rather than concentrated at a single point. This was a genuine theoretical breakthrough. String theory was, and in many ways still is, mathematically beautiful and extraordinarily rich. But string theory has a problem. Several problems, actually. The first is that it requires extra dimensions, not the 3 spatial dimensions we experience, not the 4 dimensions of space-time, but 10 or 11 total dimensions, with 6 or 7 of them curled up into an incredibly tiny structure called a compactification manifold. The geometry of this compactification determines the physical constants, the masses of particles, the strengths of forces, the value of the cosmological constant. And the number of possible compactification geometries is staggeringly large. Estimates suggest there are something like 10 to the power of 500 possible string theory vacua, possible ways the extra dimensions could be curled up, each corresponding to a different physics, a different universe with different constants. This is not a prediction. This is the opposite of a prediction. It means string theory can describe an almost limitless variety of possible universes. To uniquely predict our universe, you need to know which of the 10 to the 500 vacua we happen to inhabit, and no one has any idea how to determine that. The second problem with string theory is that it has produced essentially no verified predictions about our universe. Not a single particle predicted uniquely by string theory has been detected. Not a single stringy effect has been measured. Not a single sharp prediction of string theory, one that could not be reproduced by some other model, has been confirmed. This does not mean string theory is wrong. A theory can be correct, and yet be so difficult to test that its confirmation eludes us. String theory operates at energy scales so far beyond anything achievable by any foreseeable particle accelerator that direct tests may be impossible in principle. But a theory that cannot be tested is, from a strictly empirical standpoint, something less than a scientific theory. It is a mathematical framework, a possible description of reality, a landscape of potential truths. Without a way to test it, it cannot be science in the full sense of the word. And this has caused a profound crisis of identity within theoretical physics. Loop quantum gravity, the main rival to string theory as an approach to quantum gravity, takes a completely different route. Instead of replacing the point particles of quantum field theory with strings, it quantizes space-time itself. In loop quantum gravity, space is not a smooth, continuous background. It is a discrete network of quantum states, a spin network, where volume and area come in discrete quantum units at the Planck scale. Space is made of atoms, not atoms in the chemical sense, but fundamental, indivisible quanta of spatial geometry. And time, rather than being continuous, advances in discrete steps. The universe is, at the deepest level, a vast combinatorial structure, a quantum graph, a network of relationships with no smooth geometry at all at the Planck scale, only discreteness and connectivity. Loop quantum gravity is mathematically consistent. It does not have the non-renormalizability problem of standard quantum gravity. It makes some tentative predictions. The universe should be opaque to very high energy gamma rays in a specific energy-dependent way. There should be no Big Bang singularity, but instead a big bounce, where the collapsing universe bounced into expansion, and primordial gravitational waves should have a specific spectrum. Some of these predictions are potentially testable with future observations, but loop quantum gravity has its own serious difficulties. Showing that it correctly reproduces the smooth spacetime of general relativity at large scales, that the smooth geometry emerges from the underlying discrete structure in the right way, has proven technically formidable, and the low-energy predictions of the theory remain difficult to compute reliably. After decades of work by brilliant people, loop quantum gravity and string theory remain two massive, unverified theoretical frameworks, each internally consistent, each with its champions and its critics, and neither yet firmly connected to the world of experiment. The situation is this: physicists do not know what space is made of. They do not know whether space is made of anything. They do not know whether space is continuous or discrete. They do not know whether time is fundamental or emergent. They do not know whether the universe has additional dimensions beyond the four we experience. They do not have a theory that correctly describes gravity at quantum scales. They have been working on this problem, the hardest problem in physics, for 100 years, and they are not close to a solution, not in the sense of being a generation away, perhaps further. Perhaps the solution requires a conceptual revolution so radical that no one has yet conceived it. Perhaps it requires abandoning assumptions so deeply embedded in current thinking that physicists do not even recognize them as assumptions. Perhaps it requires seeing something that human minds have not yet trained themselves to see. You should notice what is happening here. We started with quantum entanglement, a strange, specific, measurable phenomenon in particle physics. We moved to dark energy, a mysterious component of the universe that drives its accelerating expansion and cannot be explained by any known mechanism. We moved to dark matter, 27% of the universe that is invisible and undetected. We moved to the Hubble tension, a fundamental inconsistency in our measurement of the universe's current expansion rate. And now we have arrived at the deepest layer, the complete incompatibility of our two greatest theories, the absolute absence of a quantum theory of gravity, the theoretical darkness that lies at the bottom of every physical inquiry pushed far enough. These are not separate problems. They are facets of a single, enormous, incomprehensible problem. And the problem is not a gap in knowledge to be filled by the next generation of clever experiments. It is a structural problem, a problem with the foundations themselves. Let us be very precise about what this means. In science, when you have a theory that works, that makes predictions and those predictions are confirmed, you have done something real. You have found a piece of the truth. You have genuinely increased human understanding. The history of science is a story of accumulating true things, of building increasingly accurate maps of reality. And the remarkable thing about the current situation is not that physics has stopped working. It has not. General relativity continues to produce accurate predictions. Quantum mechanics continues to produce accurate predictions. The standard model of particle physics, the theory of quarks, leptons, and the forces that govern them, continues to make predictions confirmed to extraordinary precision. Science is not failing, and that, paradoxically, is part of the problem. Because these theories work so well in their domains that it is tempting to assume the domains simply need to be extended, that the answers will come from doing more of what we are already doing, only bigger and better and more precise. But some physicists are starting to ask whether the crisis is deeper than that, whether it is not just that we are missing some particles or some symmetries or some geometric principles, whether we are missing something more fundamental, whether the very conceptual framework within which we are asking questions, the framework of space, time, particles, fields, and forces, is itself inadequate to the task of describing reality at its deepest levels. Whether the reason we cannot find a quantum theory of gravity is not that we have not been clever enough in our mathematics, but that we are trying to fit a fundamentally non-spatial, non-temporal reality into concepts that are inherently spatial and temporal. Whether the universe at its deepest level is simply not the kind of thing that can be described in the language we have. This is where things get philosophically vertiginous in a way that goes beyond the discomfort of any particular unresolved problem. Because this is a question not just about what the universe is made of, but about the relationship between human minds and physical reality, about whether the concepts we use to understand the world, space, time, cause, effect, thing, property, relation, are features of the universe itself, or features of our cognitive apparatus. Whether the laws of physics are written into the fabric of reality, or into the way minds like ours happen to represent reality. Whether science is discovering the universe, or constructing a model that is useful but not literally true. The philosopher Immanuel Kant argued in the 18th century that space and time are not features of the world in itself. They are the forms of our intuition, the structures that our minds impose on experience, the lenses through which we perceive rather than things we perceive. The universe as it is in itself, the Ding an sich, the thing in itself, is forever inaccessible to us. We can only know the universe as it appears through the filters of our cognitive architecture. Kant's argument was philosophical, not scientific, but in the 21st century some of the most interesting physics is beginning to sound disturbingly Kantian, because the research program that is gaining the most traction in quantum gravity right now, the program that seems to be pointing towards something genuine about the deep structure of nature, is a program that puts information at the foundation of everything. And information is not a thing in the world. Information is relational. It is always information about something, for something, to something. It is irreducibly tied to the existence of a perspective, an observer, a system capable of receiving and using it. The holographic principle is a good place to start this part of the story. It emerged from the study of black holes, which are, as we will discuss in detail, the places where the crisis of quantum gravity is most acute. The holographic principle, developed in part by Gerard 't Hooft and Leonard Susskind in the 1990s, says something extraordinary. The amount of information that can be contained in a region of space is not proportional to the volume of that region. It is proportional to the area of the surface surrounding that region. The information content of a three-dimensional volume is bounded by a two-dimensional surface. The universe, at some deep level, may be a two-dimensional structure, and what we experience as three-dimensional space may be something like a projection of that two-dimensional information. This is not a vague or metaphorical claim. It is a precise mathematical statement with testable consequences. The strongest evidence for it comes from something called the ADS-CFT correspondence, discovered by Juan Maldacena in 1997. This is a proven mathematical equivalence between a theory of quantum gravity in a curved, anti-de Sitter spacetime and a quantum field theory without gravity living on the boundary of that spacetime. The bulk and the boundary are different descriptions of the same physics. Gravity in 3 dimensions is equivalent to a non-gravitational quantum field theory in 2 dimensions. The holographic duality is real, in the mathematical sense. It has been used to compute properties of strongly interacting matter, the quark-gluon plasma, high-temperature superconductors, the structure of nuclear matter, that were previously beyond the reach of any other theoretical method. It has become one of the most powerful tools in theoretical physics, but what the holographic principle implies about the nature of reality is staggering. If the physical world has a holographic description, if everything happening in a volume of space can be completely encoded in the information on a surface surrounding that volume, then the dimensionality of space is not fundamental. The three-dimensionality of our world is not a basic fact of nature. It is something that emerges from an underlying description that has one fewer dimension. Space itself, the fabric of reality as you experience it every moment of your life, the thing that gives you the sense of being located here, in this body, in this room, at this distance from everything else, is not fundamental. It is emergent. It arises from something else, something that is not spatial, something that, at its deepest level, might be nothing more or less than information. And if space is emergent, then time might be too. This is actually one of the directions that research in quantum gravity is pointing with increasing urgency. In general relativity, time is dynamic. It curves and stretches and slows near massive objects. It is woven together with space into spacetime, and the geometry of spacetime is what we experience as the flow of time and the distances between places. But in quantum mechanics, time is not dynamic. It is a fixed background parameter, a classical non-quantum label that tells you when a measurement happens. There is no operator for time in quantum mechanics, no quantum state of time, no superposition of times. The two theories treat time in fundamentally incompatible ways. And when you try to build a quantum theory of gravity, time immediately becomes problematic. The Wheeler-DeWitt equation, an early attempt to quantize general relativity, actually produces a wave function of the universe that does not depend on time at all. Time disappears. The universe, at the most fundamental quantum gravitational level, might be static, timeless. The flow of time we experience every moment of our lives might be something that emerges from this timeless quantum state, something we perceive, but that is not fundamental. If space is emergent and time is emergent, then what is fundamental? What is at the bottom? What is the irreducible ultimate constituent of reality? This is where the information theoretic program, the idea that information is fundamental, becomes compelling. Not information in the everyday sense of bits and bytes on a hard drive. Information in the deep physical sense, the relationships between systems, the correlations between states, the entanglement structure of quantum fields. There is a growing body of evidence from multiple directions in theoretical physics that spacetime geometry itself, the smooth, continuous fabric of relativity, is actually a consequence of entanglement, that the reason two regions of space are close to each other, spatially connected, is that the quantum fields in those regions are highly entangled. That spatial distance, in some deep sense, is the inverse of quantum entanglement. Regions with high entanglement are close. Regions with low entanglement are far. Disconnect the entanglement, and the spatial connection dissolves. Space tears apart. In the language of holography, this is captured in the Ryu-Takayanagi formula, a precise mathematical relation showing that the area of a surface in the bulk spacetime equals the entanglement entropy of the corresponding region on the boundary. What this means, if it is correct, is that space is woven from entanglement. The fabric of the universe, the stage on which everything happens, the background of all existence, is not a pre-existing thing that particles and fields live inside. It is built, dynamically, from the quantum entanglement between degrees of freedom. When two quantum systems are entangled, they are in a deep sense spatially connected. When they are not entangled, they are not connected. The network of entanglement is the network of space. And this means that the strangest feature of quantum mechanics, the non-local, instantaneous, distance-defying correlation of entanglement, is not an anomaly. It is not a glitch in the cosmic software. It is the mechanism by which space itself is constructed. The thing Einstein called spooky action at a distance is not a strange addition to the physical picture. It is the foundation from which the picture is built. This is the kind of idea that sounds beautiful and abstract until you start following its implications, at which point it becomes something rather more disorienting. If space is woven from entanglement, then changing the entanglement changes the geometry. Reducing entanglement between two regions makes them more distant, farther apart in space. Increasing entanglement makes them closer. Entanglement is the glue holding space together. And in quantum mechanics, entanglement is not a fixed, permanent property. It changes as systems interact and evolve, which means space is not a fixed, permanent background. It breathes. It changes as the quantum state of the universe changes. At the quantum gravitational scale, space is not a container but a consequence. Not the stage but the set, assembled and dismantled with every interaction, rebuilt and rearranged by the ceaseless quantum churn of entanglement and decoherence. This brings us at last to black holes. We have been circling them for a while now, and it is time to go there directly, because black holes are not just fascinating objects in the universe. They are the laboratories where the crisis of physics is most acute, most visible, most irresolvable. They are the places where general relativity and quantum mechanics crash into each other most violently, and the wreckage of that collision contains clues, strange, contradictory, deeply unsettling clues about the nature of reality. A black hole is a region of space-time where the curvature of gravity is so extreme that nothing, not matter, not radiation, not light, can escape. The boundary of this region is the event horizon. Cross the event horizon, and you are, classically, gone. The escape velocity exceeds the speed of light, and nothing can catch up to it. You are cut off from the rest of the universe forever. For a long time, black holes were thought to be perfectly black, cold, silent. Their event horizon's a one-way door through which everything could enter and nothing could leave. Then in 1974, Stephen Hawking did a calculation. He applied quantum field theory to the region near the event horizon of a black hole and found something nobody expected. He found that black holes are not perfectly black. They radiate. At the event horizon, quantum fluctuations of the vacuum, pairs of virtual particles constantly appearing and annihilating, are modified by the intense curvature of space-time. Occasionally, one particle of a virtual pair falls inside the horizon, while the other escapes to infinity. The black hole loses a tiny amount of mass with each such event, and the radiation that emerges, Hawking radiation, has a thermal spectrum like the glow of a heated object. The temperature of a black hole is inversely proportional to its mass. Small black holes are hotter and radiate more intensely. Large black holes are near absolute zero and radiate almost imperceptibly. Hawking radiation is almost certainly real. The physics that leads to it is based on such well-tested principles of quantum field theory and general relativity that most physicists accept its existence, even though it has never been directly observed. A stellar mass black hole has a temperature so close to absolute zero that its Hawking radiation is completely swamped by the cosmic microwave background, and there is no plausible way to observe it directly with any instrument we can build. But the fact that Hawking radiation exists in principle creates a devastating problem, the black hole information paradox. And this paradox is not a philosophical puzzle. It is a precise mathematical contradiction between two theories that we know to be true. It is, in a very real sense, the sharpest tip of the spear that is currently pointed at the heart of physics. The problem is this: when matter falls into a black hole, it carries information, not just energy and momentum, but information about its quantum state, what kind of particles it is made of, how they are entangled with each other, what their spin states are, every quantum number they possess. All of this information goes behind the event horizon. Now Hawking's calculation shows that the radiation emitted by the black hole is thermal, perfectly random, containing no information about what fell in. The radiation is the same regardless of what the black hole swallowed. If you throw in a book, a cloud of hydrogen gas, or an advanced civilization's entire digital archive, the Hawking radiation looks exactly the same. So when the black hole finishes evaporating, when it has radiated away all its mass and disappears, where did the information go? This is not a vague philosophical worry about where things go when they are destroyed. It is a sharp technical problem about a foundational principle of quantum mechanics. Quantum mechanics is unitary. The evolution of a quantum state is governed by equations that preserve information. The total information content of a closed quantum system never increases or decreases. It can be scrambled, redistributed, made practically impossible to extract, but it cannot be destroyed. This is not a minor technical feature of quantum mechanics. It is a deeply fundamental principle. Destroy unitarity, and you destroy the entire mathematical framework. You make quantum mechanics incoherent at the most basic level. Energy would not be conserved. Probabilities would not add up to one. The theory would become self-contradictory. So you have two choices, and neither of them is acceptable. Either the information is destroyed when the black hole evaporates, which violates quantum mechanics, or the information somehow escapes in the Hawking radiation, hidden in subtle correlations that Hawking's calculation missed. The second option seems more appealing because at least it preserves quantum mechanics, but it creates its own catastrophe, because for the information to escape in the Hawking radiation, the radiation cannot be truly thermal. It must carry subtle quantum correlations. It must be entangled with the infalling matter behind the horizon. But Hawking radiation is produced near the horizon, in the region just outside the black hole. How can it be entangled with matter that is already inside? The matter crossed the horizon before the radiation was emitted. How does information get from inside to outside when nothing can cross the event horizon in the outward direction. The two most prominent proposals for resolving this paradox are the firewall and black hole complementarity. Black hole complementarity, proposed by Susskind and others in the 1990s, says that the information both falls in with the infalling matter and escapes in the Hawking radiation. But this does not violate any physical principle because no single observer can see both copies. From the outside, the information seems to escape in the Hawking radiation. From the inside, the information falls in with the matter. These two descriptions are complementary in the quantum mechanical sense. They apply to mutually exclusive situations, and no experiment can verify both simultaneously. This is an elegant idea, drawing on the spirit of quantum complementarity in particle physics. But in 2012, a group of physicists, Ahmed Almhiri, Donald Marolf, Joseph Polchinski, and James Sully, collectively known as AMPS, showed that complementarity might not actually work. The AMPS argument is subtle, but devastating. It uses the monogamy of entanglement, the quantum mechanical principle that if particle A is maximally entangled with particle B, it cannot also be entangled with particle C. The argument shows that if you require the Hawking radiation to be unitary, to carry information in a way consistent with quantum mechanics, and if you require the infalling observer to experience nothing unusual at the horizon, no dramatic effect as they cross what should be a smooth, unremarkable region of spacetime, then you get a contradiction with the monogamy of entanglement. To reconcile the two requirements, you would need to allow a single particle to be maximally entangled with two different systems simultaneously, which is forbidden. The way out of this contradiction, AMPS suggested, is dramatic. The event horizon is not smooth and unremarkable. Instead, it is a wall of energy, a firewall, that incinerates anything that attempts to cross it. The infalling observer is burned to a crisp at the horizon, not at the singularity inside. The firewall proposal resolves the information paradox at the cost of destroying what Einstein called the equivalence principle, the foundational principle of general relativity that says a freely falling observer should not experience any local effects of gravity. In the reference frame of a freely falling observer, space-time should be locally flat, indistinguishable from Minkowski space. The firewall violates this. It says that the event horizon is a special, physically distinct surface, not just a coordinate artifact. It means that the geometry of space-time around a black hole, as experienced by an infalling observer, is fundamentally different from what general relativity predicts. It means that general relativity breaks down not at the singularity as we knew it must, but at the event horizon, a macroscopic surface, potentially light years across for a supermassive black hole, where classical space-time is supposed to be perfectly smooth and well-behaved. So here's the cage. Unitarity, the conservation of information, is a bedrock principle of quantum mechanics, and violations of it are catastrophic. The equivalence principle is a bedrock principle of general relativity, and violations of it at the horizon are deeply troubling. If you preserve both, you get a contradiction. If you sacrifice unitarity, you break quantum mechanics. If you sacrifice the equivalence principle at the horizon, you break general relativity. There is no currently known theoretical framework that resolves the black hole information paradox without breaking one of these foundational principles. And this is not a problem that has been quietly shelved while physicists wait for new data. It is one of the most intensely debated problems in theoretical physics right now, drawing in some of the greatest minds in the field, producing some of the most creative and radical ideas in the history of physics. One of the most recent and remarkable developments in this area is something called the island formula and the Page curve. The Page curve, named after physicist Don Page, is the predicted curve showing how the entanglement entropy of Hawking radiation should behave over time if information is preserved. It should start low, rise to a maximum at the Page time, roughly halfway through the evaporation, and then decrease back to zero as the black hole finishes evaporating, and all the information is eventually encoded in the radiation. For decades, Hawking's calculation predicted something different. The entanglement entropy should rise monotonically and never decrease, which is inconsistent with unitarity. In 2019, using techniques from the holographic correspondence and a new concept called quantum extremal surfaces, researchers were able to derive the Page curve from first principles to show, using a semi-classical calculation with quantum corrections, that the entanglement entropy of Hawking radiation does in fact follow the unitarity-preserving curve. This was celebrated as a major breakthrough. Headlines declared that the information paradox had been solved. but the celebration was premature. Because deriving the right curve is not the same as understanding the mechanism, the calculation works by including contributions from regions inside the black hole, the so-called islands, in the calculation of the entropy. These island regions are disconnected from the exterior of the black hole in the ordinary sense of space-time connectivity, yet they contribute to the entropy of the outside radiation. And the reason they can contribute, the mechanism by which information escapes from the inside to the outside, remains completely mysterious. The answer is right. The mechanism is unknown. Physics has, in a very literal sense, derived the correct result without understanding why it is correct. And that is perhaps the strangest scientific situation of all, to have the answer, but not the understanding. To hold the solution in your hands and have no idea what it means. There is a concept that threads through all of this, through the information paradox, through the holographic principle, through the entanglement structure of space-time, through the measurement problem in quantum mechanics, and it is the concept of the observer. Not the observer in the colloquial sense of a person watching something, the observer in the deep physical sense, any physical system that acquires information about another physical system, any interaction that results in a correlation between two systems, any process that, in the language of quantum mechanics, constitutes a measurement. The observer, in this sense, is not peripheral to the physics. It is not something you can peel away from the description of nature to get to the pure, observer-independent truth underneath. It is built into the structure of quantum mechanics at the most fundamental level. And as you go deeper into the problems we have been discussing, the observer keeps appearing. In the measurement problem, in the relational interpretation, in the holographic principle, in the information paradox, in the page curve calculation, everywhere you find the deepest unsolved problems in physics, you find lurking in the background the unresolved question of what an observer actually is and what role observation actually plays in determining what is real. John Wheeler, one of the greatest physicists of the 20th century, spent the last decades of his life trying to articulate an idea. He called it from bit, the proposal that physical reality is, at its core, informational, that every particle, every field, every dimension of space and time derives its existence from binary choices, from yes or no questions, from acts of observation that establish facts. He was not claiming that the universe is made of computers or that reality is a simulation. He was making a deeper claim that the act of asking a question of nature, the act of a physical system interacting with another physical system in a way that establishes a fact, is not something that happens inside reality. It is something that constitutes reality. The universe is not a collection of things that observers happen to look at. The universe is a collection of observations, of interactions, of established facts. The things are secondary. The facts come first. This idea that information is more fundamental than matter, that facts are more fundamental than things, that the universe is built from observations rather than the observations being built inside the universe, is difficult to hold in your mind. It resists the grain of ordinary thinking. Every instinct you have says that the world was there before you were, that the stars burned and the planets turned for billions of years before any mind existed to observe them, that reality does not need observers to be real. And at the macroscopic scale, at the level of stars and planets and everyday objects, this intuition is effectively correct. The quantum indeterminacy that makes observation so philosophically fraught is washed out at large scales by decoherence, the process by which quantum superpositions collapse into definite classical states through interactions with the environment. A rock does not need to be observed to be in a definite location. It interacts with so many other particles every second that its quantum state is effectively determined by those interactions continuously, whether or not any conscious being is paying attention. But at the foundational level, at the level of individual quantum systems, at the Planck scale, at the level of the universe as a whole, the situation is different. And the universe as a whole presents a particular challenge, because quantum mechanics, as usually formulated, requires an observer outside the system to collapse the wave function, to establish definite facts. But if the system is the entire universe, there is no outside. There is no external observer. There is no environment for the universe to decohere into. The universe is closed. Its quantum state, the wave function of the universe, has no external reference point, no outside measurement, no classical apparatus to collapse it into something definite. And this is not just a technical inconvenience. It is a fundamental conceptual problem with applying quantum mechanics to cosmology. It is the reason that quantum cosmology, the attempt to describe the origin and evolution of the universe using quantum principles, is so philosophically fraught. The observer cannot be outside the system. The observer is part of the system, and that changes everything about what observation means, and what facts are, and what reality consists of. Let us step back now and look at the full landscape of what we have covered, not to summarize it neatly but to feel its shape. You began with quantum entanglement and the measurement problem. You moved through dark energy and the cosmological constant problem, with its incomprehensible 120 order of magnitude discrepancy. You passed through dark matter and its stubborn refusal to be directly detected despite decades of heroic experimental effort. You encountered the Hubble tension, the growing crack in our standard cosmological model that refuses to close despite increasingly precise measurements. You descended into the incompatibility of general relativity and quantum mechanics, the theoretical void at the Planck scale, the failure of string theory and loop quantum gravity to deliver a confirmed, predictive theory of quantum gravity. You looked into black holes and found the information paradox, where quantum mechanics and general relativity directly contradict each other with no currently known resolution. And you arrived at the deepest level, where the role of the observer, the nature of information, and the emergence of space and time from entanglement point toward a picture of reality so alien to ordinary intuition that it barely qualifies as a picture at all. And now something else needs to be said, something that is rarely stated this plainly, because stating it plainly makes scientists uncomfortable, and rightfully so, because it sounds like the kind of thing that invites misunderstanding and misuse. But it is the honest conclusion of the evidence, and to flinch from it would be intellectually dishonest. The honest conclusion is this: we do not know what the universe is, not in the sense of missing a few details at the edges of an otherwise complete picture. In the sense that the central core of the picture, the nature of space, the nature of time, the nature of matter, the mechanism of quantum measurement, the constitution of 95% of the universe's energy content, is unknown. We have extraordinarily accurate mathematical models of how things behave. We have extraordinarily precise measurements of what things do. But what they are, what reality actually is at the deepest level, is a question to which we have no answer. Not a partial answer being refined. No answer. This is not a failure of science. It is the current state of science. And the difference between those two things is not just semantic. Science has always proceeded by successive approximation, by building models that work well within certain domains and then finding the cracks where they break down, and using those cracks to guide the next generation of models. Newton's mechanics worked brilliantly until it encountered velocities close to the speed of light and was superseded by relativity. Classical electromagnetism worked brilliantly until it encountered the behavior of matter at atomic scales and was superseded by quantum mechanics. Quantum mechanics and general relativity each work brilliantly within their own domains, and the cracks between them, the black hole information paradox, the cosmological constant problem, the measurement problem, the incompatibility of their foundational assumptions, are the indicators that another supersession is coming, another revolution, another radical reconceptualization of what the universe is and how it works. The cracks do not mean the science is broken, they mean the science is alive. But this revolution, when it comes, will be unlike any that preceded it, because every previous revolution in physics replaced one model of the world with a better, more accurate, more encompassing model, while leaving untouched the assumption that the world is something that exists independently of being modeled, that there is a mind-independent reality out there, that the job of physics is to describe it, that the truth of a physical theory is a matter of its correspondence to that independent reality. The coming revolution, if the hints are to be believed, may require giving up that assumption, or at least deeply revising it. Because if space-time is emergent, if the observer is not separable from the observed, if information is more fundamental than matter, then the relationship between the model and the reality is no longer simple correspondence. The model is not a description of something that exists independently of the modeling. The modeling is part of what constitutes the reality. There is a version of this that sounds like philosophical idealism, the old philosophical position that reality is mental, that nothing exists outside of minds that perceive it, and most physicists working on these ideas are careful to distance themselves from that interpretation. They are not saying that the universe is a thought, or that rocks and stars exist only because conscious beings are thinking about them. They are saying something more subtle and more technical. that the fundamental constituents of reality are not things with intrinsic, observer-independent properties, but relational structures, patterns of information, networks of entanglement, webs of mutual influence and correlation, that the thingness we attribute to particles and fields and space-time geometries is something we construct from these relational structures by inhabiting a particular perspective, a particular scale, a particular coarse graining of the underlying information. The things are real, the experience is real, but the thingness is not fundamental. It is a useful, accurate, stable feature of our perspective on something deeper that does not look like things at all. Think about what it means to say that space emerges from entanglement. You are sitting wherever you are reading this. The distance between you and the screen, between you and the wall, between you and every other object in the room, that distance feels absolute. It feels like the most basic, bedrock fact of your existence. You are here. Other things are there. Space is the container within which everything is located, and your location in it is the most fundamental thing about you as a physical object. But what we are now being told, what the mathematics of holography and the Ryu-Takayanagi formula and the entanglement structure of quantum fields is telling us, is that this distance, this space, this container is not fundamental. It is built from something else, something non-spatial, something that, at its base level, has no concept of here or there, near or far, inside or outside. The space you are sitting in right now is an emergent property of an underlying quantum information structure that does not itself occupy any space, and your sense of being located, your sense of being here, is a feature of a particular perspective on that structure, not a fundamental fact about the structure itself. This is the moment where language starts to fail, because language is built for the world we experience, the world of things and places and distances and times, and trying to describe a reality that is more fundamental than space and time using words designed for a spatial and temporal world is like trying to describe color to someone who has never had eyes. The best we can do is point in the direction of the truth, using metaphors that approximate it without reaching it. The universe at its deepest level is more like a vast, seething network of relationships than like a collection of objects in a container, more like music than like matter, not because it is insubstantial, but because its identity is in its structure, its pattern, its relational organization rather than in any intrinsic properties of its parts, more like a story than like a photograph, not because it is fictional, but because it is a sequence of meanings that depend on each other, that gain their content from their context, that cannot be reduced to the properties of individual words. And here is something that almost never gets said, but that follows directly from everything we have been discussing. If this picture is even approximately correct, then the question of what exists, the most basic question of all, becomes profoundly ambiguous. In classical physics, the question has a clear answer. Things exist, out there, in space, with definite properties. In quantum mechanics, the answer is less clear. Things exist in superpositions of states, and definite properties emerge only through interaction and measurement. In the information theoretic picture, the answer becomes, what exists is a structure of relationships, and the things we normally say exist, particles, fields, space-time, are stable, coarse-grained features of that structure that we encounter from our particular perspective. There is no view from nowhere. There is no God's eye description of what exists. There are only perspectives, each accurate within its own domain, each incomplete when taken alone, none privileged over the others. And yet, and this is crucial, this does not mean that anything goes. It does not mean that all perspectives are equally valid, that there are no objective truths, that science is merely one narrative among many. The structure of relationships is real. The patterns of entanglement are real. The mathematical laws governing quantum states are real. The predictions of general relativity are real. The conservation laws, the symmetry principles, the causal structure, these are all real features of the relational structure underlying the universe. The fact that space-time emerges from something more fundamental does not make space-time less real. The fact that particles are excitations of quantum fields does not make matter less real. Reality is not less real for being relational rather than thing-like. It is differently real, and that difference, that subtle but profound shift in what we mean by real, is perhaps the deepest implication of everything we have been discussing. We should talk about one more thing before we reach the edge. One more layer of the impossible that deserves to be named plainly, something that is not usually spoken about in the same breath as quantum mechanics and dark energy, because it sounds more speculative, more philosophical, more like the kind of thing that belongs in a different kind of video entirely. But the physics, honestly pursued, leads here. and ignoring it for the sake of maintaining a respectable scientific tone would be a kind of dishonesty. The thing is this: the universe, as far as we can tell, is precisely calibrated for the existence of complexity, for the existence of stars, planets, chemistry, life, and minds capable of doing physics. And the calibration is extraordinary, not approximate, not rough, not in the ballpark. Extraordinary. The kind of precision that, when you look at it directly and let yourself feel its full weight, produces a sensation that is hard to name but is somewhere between wonder and unease. The fundamental constants of nature, the speed of light, the mass of the electron, the strength of the gravitational force, the strength of the electromagnetic force, the mass of the Higgs boson, the value of the cosmological constant, the ratio of the strengths of the strong and weak nuclear forces, are not derived from any deeper principle we know of. They are, as far as current physics is concerned, simply numbers, brute facts. They have the values they have, and there is no known reason why they could not have been different. And if you change them, even slightly, even by fractions of a percent in some cases, the universe becomes sterile. Change the strength of the strong nuclear force by a few percent and either hydrogen is the only element that exists, because nuclei cannot bind, or all hydrogen fused almost instantly after the Big Bang, leaving no fuel for stars. Change the cosmological constant by even a small fraction of the enormous value predicted by quantum field theory, and either the universe collapsed back on itself before any structures could form, or it expanded so rapidly that matter could never clump together into galaxies, stars, or planets. Change the mass ratio of the proton to the electron, and chemistry as we know it is impossible. Change the dimensionality of space, and stable orbits do not exist. This is what physicists call the fine-tuning problem, or sometimes the anthropic coincidence. The universe appears to be fine-tuned for complexity. The constants that govern its behavior happen to lie in a narrow range that permits the existence of the elaborate structure, atoms, molecules, cells, brains, that are necessary for the universe to be observed by anyone. Some physicists respond to this with the anthropic principle. Of course, the constants are compatible with our existence, because if they were not, there would be no us to observe them. We are, inevitably, in a universe that permits us to exist. This is technically true, but many physicists find it deeply unsatisfying, because it does not explain why the universe is fine-tuned. It just explains why, given that it is, we are here to notice. The anthropic principle is not a mechanism. It is a tautology dressed in scientific language. The most popular physical mechanism proposed to explain fine-tuning is the multiverse, the existence of an enormous number, perhaps infinite, of separate universes with different values of the fundamental constants. If there are enough universes, some of them will have constants compatible with complex structures and observers. We inevitably find ourselves in one of those universes. The multiverse makes the fine-tuning unsurprising without requiring any special mechanism. But the multiverse comes at a price that many physicists find prohibitive. It is, by construction, unobservable. The other universes in the multiverse cannot interact with ours, cannot send signals to ours, cannot be detected by any instrument in our universe. They are, in the strict empirical sense, beyond science, and a proposed explanation that invokes an infinite number of entities that are forever beyond the reach of any possible observation is not obviously an improvement over having no explanation at all. Some physicists accept it as the best available option. Others find it deeply unsatisfying. The debate has no end in sight. There is another possibility, a possibility so radical that most physicists resist naming it, because naming it invites a torrent of misunderstanding and association with ideas they would rather not be associated with. But intellectual honesty demands that it be stated. The possibility is this: the fine-tuning is not a coincidence. It is not explained by a multiverse. It is not the result of some deeper physical mechanism that we have not yet discovered. Instead, it reflects something about the relationship between the universe and the minds that inhabit it. Something about the fact that, in quantum mechanics, observers are not separable from the systems they observe. Something about the fact that, in the holographic and information-theoretic picture of physics, the structure of reality is constituted by the facts that are established by interactions and observations. Something about the possibility, strange, disturbing, not falsifiable in any obvious way, but not obviously wrong, that the universe is not a closed, self-contained physical system that happened to produce observers as a late and incidental byproduct, that the relationship between the universe and the minds within it is more intimate, more fundamental, more constitutive than the standard picture allows. This is not a religious claim. It is not mysticism. It is not the claim that the universe was designed by an external intelligence for the purpose of producing human beings. It is something more subtle and more philosophically precise. The claim that the concepts of observer, information, measurement, and fact, which quantum mechanics insists are not peripheral but foundational to physical reality, mean that the universe cannot be cleanly separated from the process of it being known. That the fact of being observed, so not by any particular observer, but by the existence within the universe of physical systems capable of establishing facts about it, is not something that happens inside the universe as a neutral backdrop. It is something that participates in determining what the universe is. And if that is true even approximately, even partially, then the question of why the constants are what they are, why the universe is calibrated for complexity, may not be a question about external design or cosmic coincidence. It may be a question about what it means for a universe to exist at all in the presence of observers, about what the relationship between existence and observation ultimately is, about whether a universe that produced no observers would be a universe in any meaningful sense. You have been on a long journey. You began with the certainty that science is our best map of reality, and that map is genuine and earned and extraordinarily detailed. You moved through quantum entanglement and the collapse of classical intuitions about locality and separability. You passed through the cosmological constant problem and the incomprehensible mismatch between theory and observation that it represents. You traversed the mystery of dark matter, the stubborn anomaly of the Hubble tension, the decades-long failure to reconcile general relativity with quantum mechanics, the theoretical abyss at the Planck scale. You looked into black holes and found the information paradox, which pits the two greatest theories in physics directly against each other with no resolution. You descended to the level of quantum gravity and holography, where space and time appeared to be emergent properties of an underlying entanglement structure that is itself non-spatial and non-temporal. And you arrived at the fine-tuning problem and the anthropic coincidence, where the universe's most fundamental parameters appear calibrated for complexity in a way that has no satisfying explanation within any existing theoretical framework. Each of these is individually strange, individually unsettling, individually capable of producing that particular discomfort that comes from confronting something genuinely beyond your conceptual grasp. But what makes them truly disturbing, what gives this collection of anomalies its real weight, is not any one of them in isolation. It is the pattern they form together, because they are not separate anomalies. They are all symptoms of the same underlying condition. They all point in the same direction. They all suggest in their different ways that the universe is not what we think it is, not wrong in a correctable way, not incomplete in a fillable way, but structured differently at the deepest level than any of our current frameworks can accommodate. That reality, whatever it is stranger and more fundamental and more alien to ordinary intuition than 4 centuries of science have yet been able to reveal. And here is the thing that should stay with you after everything else fades, the thing that, if you hold it clearly in your mind, produces not despair or nihilism, but something closer to awe, mixed with genuine unease. Physics is not at the end of its story. It is not a completed building with a few cracks to be patched. It is more like a vast, beautiful structure, erected on a foundation that, when examined closely, turns out to be not entirely solid. The structure is real. The achievements are real. The predictions are real. The technology built on the science, the semiconductors, the lasers, the MRI machines, the GPS satellites, the entire technological civilization is real. None of that disappears. But underneath it all, at the very foundation, there is something that we do not understand, something that our best theories contradict each other about, something that, when pressed on hard enough and far enough, opens into a void where our concepts lose their grip and our equations break down, and the universe stares back at us in a silence that contains no answer we are yet equipped to hear. The scientists who discovered these anomalies did not set out to find the impossible. They set out to confirm what they expected to find, to fill in the remaining digits of constants already known to be roughly what they are, to sharpen the picture that was already mostly clear. And instead they found dark energy accelerating the universe's expansion. They found dark matter that nothing can detect. They found a Hubble constant with 2 irreconcilable values. They found entanglement that defies locality. They found a vacuum energy that is off by 120 orders of magnitude. They found black holes that destroy information, or firewalls that violate relativity, with no third option in sight. They found, in short, that the universe they were measuring was not the universe they thought they were measuring. They found that what they knew was not as complete as they had assumed. They found that at the bottom of every deep question, there is another deeper question, and at the bottom of that one, there is not an answer but an opening, a threshold that current physics cannot cross, beyond which lies something we have no name for and no theory to describe. The instruments will get better. They are getting better already. The James Webb Space Telescope is revealing the universe's earliest galaxies in detail that was unimaginable a decade ago, and some of those early galaxies are already surprising us, appearing larger and more structured than the standard model of cosmology predicts they should be at their redshifts. The next generation of gravitational wave detectors will listen to the universe's most violent events with sensitivity orders of magnitude beyond LIGO, the Einstein telescope, the Cosmic Explorer, the LISA mission in space. These instruments will map the gravitational universe with a fidelity that will almost certainly reveal new anomalies, new inconsistencies, new signals that do not fit the model. Future dark matter experiments will either find the particle at last, in whatever form it takes, or eliminate enough of the remaining parameter space that the particle interpretation becomes untenable, forcing physics into a confrontation with modified gravity or some third option not yet seriously contemplated. Future observations of the cosmic microwave background will sharpen the Hubble tension into either a clear resolution or an undeniable crisis. Future quantum computers will simulate aspects of quantum gravity, using the holographic correspondence to probe the deep structure of space-time through the mathematics of strongly correlated quantum systems. The science will advance. It always advances. But the deeper the instruments probe, the deeper the questions become. That has always been true in physics, and there is no reason to think it will stop being true now. The history of science is not a story of questions being answered and then the questioning ending. It is a story of questions being answered, and thereby revealing more questions, deeper questions, stranger questions. Newton answered the question of planetary motion and revealed the question of what gravity is. Einstein answered the question of what gravity is and revealed the question of what quantum gravity is. The genome was sequenced and revealed the question of how genes are regulated, and how protein folding works, and how epigenetic information is transmitted, and how consciousness arises from neural activity. Every answer is a door, and every door opens onto a larger room than the one before. The questions do not get smaller as we go deeper. They get larger, they get more fundamental, they get closer to the things we assumed were settled and were not. And somewhere in that processing, somewhere in the increasing depth and strangeness of the questions that physics is being forced to ask, is a revolution that has not happened yet. A reconceptualization so fundamental that it will make the Copernican revolution, the Newtonian revolution, the quantum revolution look like adjustments. A shift not just in what we think the universe is made of, but in what we think existence means, what we think reality is, what we think the relationship between mind and matter actually consists of. A shift that will require giving up something so deep and so assumed that most people alive today do not even know they are assuming it. Something that will seem, in retrospect, like the most obvious thing in the world to have questioned. Just as it seems obvious now that the Earth is not the center of the universe, that atoms are real, that time is not absolute. Obvious in retrospect, invisible in prospect, hidden in plain sight, the way the most fundamental assumptions always are. We do not know what that assumption is. We do not know what will be given up or what will replace it. We do not know whether the revolution will come from a new experiment, a new mathematical insight, a new theoretical framework, or some completely unexpected combination of all three. We do not know whether it will come in 10 years, or 100 years, or 1,000 years, or whether the human mind, evolved for navigating a savanna, foraging for food, and building social relationships, is even equipped in principle to conceive the truth that the universe is trying to show us. The cognitive limits of human minds are real. The concepts available in human language are real. The evolutionary history that shaped our brains for environments very different from the quantum gravitational Planck scale is real. There is no guarantee that a mind produced by evolution on a small planet orbiting a middle-aged star in the outer arm of a spiral galaxy has the cognitive architecture to comprehend the deepest structure of reality. There is no guarantee that the universe is the kind of thing that minds like ours can fully understand. And yet, and this is perhaps the most astonishing thing of all, the thing that sits at the center of all of this and refuses to be explained away. We got this far. We are an evolved primate species on an insignificant rock in an ordinary galaxy, and we have discovered quantum mechanics and general relativity and the Big Bang and the structure of DNA, and the existence of dark energy and the holographic principle in the information paradox. We have built instruments that can detect gravitational waves from black hole mergers a billion light years away. We have mapped the cosmic microwave background to a precision of 1 part in 100,000. We have collided protons at energies that reproduce conditions a fraction of a second after the Big Bang, and measured the properties of the particles that emerged. We have deduced the existence of dark matter from its gravitational effects on objects billions of light years away. We have proven mathematical theorems of breathtaking elegance and depth. We have gotten, in short, very far. Far enough to see the shape of what we do not know. Far enough to feel the edge of the possible. Far enough to find the impossible. And the impossible is there, not as a metaphor, not as a rhetorical flourish, as a fact, as something measured and confirmed and replicated by thousands of independent researchers using the finest instruments ever constructed by human civilization. The universe is accelerating, driven by a force we cannot explain and an energy we cannot account for. 95% of it is invisible to every instrument we have, constituted of substances we cannot directly detect. Its rate of expansion disagrees with itself depending on how you measure it. Its most fundamental constituents behave non-locally, instantaneously correlated across any distance in defiance of every classical intuition about the separateness of distant things. Its black holes pose an irresolvable contradiction between its two greatest theories. Its deepest structure appears to be non-spatial, non-temporal, constituted of information and entanglement rather than matter and geometry. Its fundamental constants are calibrated with extraordinary precision for the existence of complexity, without any known physical reason why they should be. And its most fundamental theory, quantum mechanics, the most precisely verified theory in history, contains at its core a problem so basic and so unresolved that physicists cannot agree on what the theory says about the nature of reality between measurements. You are not at the end of this story. No one is. You are somewhere in the middle of a mystery so large that none of the people alive today may live to see its resolution. You are in the position of a medieval scholar who knows that the universe is larger than anyone has mapped, who has instruments capable of seeing things that the previous generation could not, who understands enough to know precisely how much is not understood. You are in the position of a person standing at the edge of a known map, looking into uncharted territory, holding instruments that are not yet capable of illuminating it, hearing, just barely, from the darkness beyond the edge, something that sounds like an answer to a question you do not yet know how to ask. The scientists who found these impossible things did not despair. The best of them, the ones whose names will be remembered alongside Newton and Einstein and Bohr and Dirac, became more awake, more attentive, more scrupulous, more creative, because finding the impossible is not a defeat. It is a summons. It is the universe saying, you are close enough now to see that you are wrong, and being close enough to see that you are wrong means you are closer to the truth than you have ever been. The map is wrong. The map has always been wrong in some way. Every generation of scientists has worked with a wrong map and improved it, and passed a less wrong map to the next generation, and that process is not ending. It is accelerating. It is deepening. It is becoming, with each passing decade, more radical in its implications and more alien in its conclusions. But here, at the very edge of what science has found, something must be said that goes beyond the science. Because what these discoveries reveal, not the details, not the mathematics, not the specific models, but the revelation at their core is something that concerns every human being alive, not just the physicists who discovered it. What they reveal is that reality is more than we thought, not bigger in the sense of more galaxies or more particles or more dimensions, though it may be all of those things, bigger in the sense of more fundamental, more irreducible, more resistant to being fully contained in any model, any theory, any framework that minds like ours have yet constructed, or perhaps can construct. The universe is not a puzzle to be solved by a sufficiently clever species. It is a mystery to be inhabited, a mystery that produces in those who look at it honestly and directly and without flinching, not despair, but a kind of sober, quiet, open-eyed wonder, the wonder of a creature that has evolved the capacity to ask questions that the universe does not yet answer, and to feel, in that silence, not nothing, but the full weight of what is there. Something impossible is real. It has been measured. It has been confirmed. It refuses to go away. And the reason it refuses to go away is not that science has made an error, not that the instruments are flawed, not that the researchers were mistaken. It refuses to go away because it is pointing at something deep, something that current physics cannot see past, cannot theorize around, cannot mathematical trick its way through. Something that, when you look at it long enough, and carefully enough and honestly enough, begins to look less like an obstacle and more like a door A door in the wall of the known. A door beyond which is not empty darkness but something real, something there, something whose outline can almost be perceived in the light that leaks around its edges, something that, if we are patient enough and honest enough and creative enough, we may one day find the language to describe, and that day will change everything. It will change what we think the universe is. It will change what we think we are. It will change what we think is possible, and what we think existence means. And none of us sitting here now on this side of that door can know what we will find when it finally opens. We only know, with absolute certainty, with all the weight of measured data and mathematical contradiction and physical law pushed to its breaking point, that something is there.